Okay, good morning everyone to this course. So this course is running over four mornings from 10 to 12. I've not given these lectures before, so I'm not 100% given the exact timetable, but we will start now and we'll finish by midday. There'll be an introductory, couple of introductory lectures, then a very short practical session. The practical session is just to the main idea of this course is you do the exercises in your own time, and then you can ask us questions at subsequent lectures. But I'm going to have a very short practical session just to check that people can log on and compile and run very simple programs, and then there'll be a lecture about architecture. So this morning is going to be very much an overview, but I'll just give a quick overview to the whole course first of all. So all the material is available from the web and will be there after the course. So this course is provided as part of the ARCHER2 service. ARCHER2 is the current UK national supercomputer for EPSRC, operated by UKRI. It's housed, operated and supported by RCPCC, and the hardware is supplied by, well, it's not also by Cray, it's now HPE. But as part of running that service, we do training by the computational science and engineering team, the support team, and that's about 60 days per year at various locations, including online, obviously, and it's free to all academics. So these are the resources. Hopefully everything for this course will kind of be pre-packaged, so you won't need to look at this, but there is a lot of material there, training courses and documentation. So who are we? This course is given by a bunch of people. My name's David Henty, and you'll see coming up William, Luca, Michael, and Mark. I have a role in training at EPCC, in particular in charge of the on-campus MSc programs. There's a feedback form at the end. Please fill that in. We like feedback. Good feedback is great. It makes us look good, and we can tell episodes how wonderful we are. But we do review all the feedback. So so critical feedback is equally good because it allows us to improve the courses, and we do read the feedback and act on it. As I said here, I am going to be promoting our MSc. If any of you teach students or anyone, they might be interested in coming along. You've been given access to a project called TA200 for the course. There's a small amount of budget here. Other ARCHER2 accounts can be used. There's nothing particularly special about that project. The accounts will be closed a few weeks after the access ends, and your files will be deleted. So take copies of all your work beforehand. You'll get a warning about it, but please do that. But the main thing is, don't worry about the course material. The course material will be available from the ARCHER2 website as far as going into the future. As a code of conduct, just a general thing, we expect everyone to be welcoming, respectful, take criticism, focused on what's best, and be courteous and respectful. We all have very different backgrounds, very different levels of experience. Some of you will have done a lot of this stuff before. Some of you will be totally new. So we're just here to try and learn and learn useful skills. But if there are any incidents you're concerned of, there is a reporting form available from that URL. So the timetable is session 1 is this overview about GPU programming APIs, software, and also something about the hardware. Then other people, I'm not only teaching this morning, other people talking about the specifics of OpenMP, advanced topics, and a bit about OpenACC, but we'll cover all these going forward. The lecture notes are available on the ARCHER2 site, and just follow the links. I'll go through this later on just to make sure everyone knows where the material is. The source code is available in that directory. If you do take a copy of that, you may want to keep taking a copy, because I think some of my colleagues may be updating the material, but that is where it will be available. I hope you enjoy the course. Please ask questions. So that's one of the issues about online courses. They can unfortunately be less interactive. But if you have a question, I mean, I'm quite happy to take questions as we go along. As I say, the material will be up there for forever, for a long time in the future. So, want to make use of the time when you're online and staff are online as well. If you ask anything in the chat, I will get a notification. I'll see it, and then we can use audio or chat. It's up to you. But if you answer a question, it would be great. I would like you to ask it as soon as possible, there and then during the lecture, so we can discuss it at the right time. And there's a chat box there. Please ask questions, and then we can go to audio if that is useful. Okay, so I will just very briefly just make sure that you know where the material is. So hopefully that's the okay. So you just go to the ARCHER2 web page, to training, coming training. You'll have seen this. There's the list of our courses. But moment you'll see GPU programming use directives. Now this, after the course is finished, this will move into the past courses repository, which is another link here. Past course materials. But at the moment it's ongoing, so it's in this list. And if you click there, you'll see that we go to a web page, and there's all the stuff there. But here there's a link to the course materials and the course chat. This I'm not going to be using this in this course, but this is a persistent chat. I'd rather for this interactive course just use the chat in the collaborate box. But there's course materials here, and you'll see that the slides are available. The slides for today and the exercises are available as well. Yeah. So hopefully that will give you access to material. So this is where the slides and things are for reference. So I'll now give the first technical talk, which is going to be talking about programming interfaces for programming GPUs. So I just wanted to do maybe a quick poll. So could you answer yes or no? I just wonder if people have used ARCHER2 before. Okay, so most people haven't. That's not an issue. This is not a course about ARCHER2. It's a course about GPU programming using directives, which we'll see is portable for different architectures. That's one of the reasons we're doing it. I'm just interested in if you. Okay, that's useful to know. But the exercises are available. You should be able to run the exercises elsewhere, but for this moment they're packaged on ARCHER2. That's useful. Okay, so another question is, I'm wondering what people experience before is whether anyone has any experience of GPUs before. Typically CUDA is the model which people use. I'm just interested if people have used that, just to give me some background. Okay, so that's very interesting. Most people haven't. That's fine. That's useful to know. I said we don't assume that, but it's useful to know that as a background. And the final question I wanted to ask was whether people have used OpenMP before, whether anyone's written any parallel OpenMP programs for CPUs. Now, okay, so that's very interesting. Most people have. Again, we don't really assume that, but that's very useful to know as a background. Okay, so most people haven't used ARCHER2. Most people haven't done CUDA, but most people have done a bit of OpenMP beforehand. So that's very useful. Thanks very much. So what I will do is I will now actually give the... So I'm going to talk briefly about the models there are for programming GPUs. So this is one of the reasons we're running this course, is that if you want to program a GPU, there's a bewildering variety of APIs, application programming interfaces, to program them. What's the best to use? We'll talk about OpenMP and actually OpenACC as well on this course. There's things called CUDA, Raja, HIP, Cocos, OpenCL, SYCL. It's really quite bewildering. So a lot of this is sort of historical, but we'll try and cover what they are in this lecture and sort of put them in context so you can see, and then maybe discuss a bit why we're focusing on programming using directives. So we'll try and explain the differences and similarities between them. We'll be focusing on the common base language, C, C++, and Fortran. Now, we won't cover Python, Julia, or machine learning frameworks. I mean, there are interfaces to Python, but we're going to cover the baseline, the standard-based programming language, C, C++, and Fortran. And we'll look at the three basic programming styles, which are directives, kernels, and frameworks. And we'll talk about what languages they support, how portable they are across different platforms, how they can interact with other programming models or with system libraries, and whether they're open standards or proprietary, and who looks after them. So it's just an overview to try and put things in context. So there's really sort of three distinct programming styles when we're going to be programming GPUs: kernels, directives, and portability frameworks. So in the kernels approach, which is, for example, the one used by CUDA, what the programmer does is you write a function, typically quite a small function, typically called a kernel. It's a fairly small function, or in C++, lambda, which is the code you want to execute on the GPU. And then there's some framework which executes that code on every thread of the GPU. And so there's no explicit loop. The loop is implicit. You write a function and say, please execute this function on all the GPU threads. As we'll see going forward, there are many thousands of GPU threads. But the way that the GPU programming works is you have for a GPU, you also have a CPU. So we run the program on the CPU. So we run a standard CPU program, and we pass the function to some method that is able to basically offload that. So you run a program on the CPU, but whenever you want to do something on the GPU, you have some way of saying, here's my function. I don't want to run this function on the CPU. I want you to offload it and run it on the GPU. And that does the controls, the GPU-specific controls, the number of threads, and other such like things. There's also data movement. We'll see that GPUs and CPUs typically have different memory spaces. So explicitly, you will have to say, please copy this data from the CPU to the GPU. And then after you've done the calculation, please copy this data back from this array or these variables back from the GPU onto the CPU. That's the kernels approach. The directives approach, which is much more like OpenMP, but it's like OpenMP, is you write what looks like a normal CPU program, and then having written that, you annotate the code. So you identify blocks of code which you want to be executed on the GPU, typically performance critical pieces of code. And you have directives, offload directives, which say, please take this code and don't run it on the CPU, run it on the GPU. And then the code block will be executed on the GPU, and typically you're parallelizing a loop. And so in some way, the loop iterations will be spread over GPU threads. That will be very familiar to those of you who've done OpenMP on the CPU. The only difference is that you have at least an order of magnitude more threads available. And you control the number of threads, and the data movement is done via clauses in a sort of analogous way to we have shared and private data. For CPU, there's also an extension which allows you to take data and copy it between the CPU and the GPU memory. So so the directives is sort of based on a sort of top-down approach. You take a loop and you say parallelize this. The kernels is more like a bottom-up approach. You say, I want this function to be executed by every GPU thread, and please do that for me. Portability frameworks are almost like a different language. You basically you specify some abstract parallel execution. You have some loop and you say, I would like this to be executed in parallel, and you may specify what the data layout is, how the data is laid out, and the framework then takes that and can generate code to run on the CPU or a GPU. So the idea is that you can have a single base code and you can generate an executable that can run either on the CPU or the GPU. And they may actually generate OpenMP or CUDA code under the hood, but you don't see that. Typically, these are restricted to C++ because they use lots of C++ templating and language extensions to make it look like effectively a new language. So they use C++ features to effectively give you a new parallel language with various constructs that allow you to say, please run this in parallel, and I'd like to run on the GPU or the CPU. So what are the pros and cons of these? Well, the kernels approach is quite low level. And so if you're interested in performance, it's not so reliant on the compiler or the runtime for optimization. You're very much in control of what you're doing. And that allows for low level tuning. So you have a lot more control over what happens at runtime, and so you're not so reliant on a mature compiler or a mature runtime support from some library. It's less familiar to HPC programmers. Again, I as someone who's done MPI and OpenMP for many years, I found the kernel's approach quite unusual. It wasn't natural to me, but I've used it. It requires more programming effort. You have to do a lot of boilerplate, well, more boilerplate code. You're in charge of a lot of the basics of data movement and such like. It also has to be less portable. We'll see that the standard frameworks for this are typically are tied to a particular architecture, to a particular manufacturer. And CUDA is the standard example of this, which is the NVIDIA kernels approach. It's called kernels because what you do, as I said, you write a very simple function typically, which is called the kernel, and then that is applied to your data and runs on all the different threads. The directive-based APIs, which are sort of like OpenMP, typically require less programming effort because you write what looks like standard CPU code and you annotate it. And it's much more familiar to HPC programmers. To me, the directives-based approaches seemed very natural because it's very similar to, at least in the way it reads, is very similar to OpenMP for CPUs. Typically, you have fewer features because they have to be portable and implemented by the compiler. They're much more reliant on compiler runtime for optimization. You tell the compiler, this is what I want to do, and basically after that, it's up to the compiler to do it efficiently. And so, if the compiler isn't very good, you won't get very good performance. If the compiler is good, you will get good performance. And that can also make it difficult to do low-level tuning. If you write a loop and run it on the GPU and the performance isn't very good, it's often hard to know what to do because you may not know exactly how the compiler has parallelized it. So there's definitely pros and cons there. Again, it's a higher level approach, which is easier, more straightforward, but may have issues in terms of performance. The portability frameworks, they're good at, they typically facilitate a single code base. As I said, you write a single program, which in principle can run on CPUs and GPUs. They will have more limited features, but they're very reliant, just like the directives approach, on compiler and runtime for optimization. Again, you say, here's a loop, I want it to run in parallel across the GPU, and then you don't really know how that's done, making it difficult to do low-level tuning. So those two cons are very similar to the directive-based approach, but they're also restricted to C++. So they use C++ features to make these GPU offload and the parallelization directives look like effectively built-in language features. So if you're not a C++ programmer, that can be quite challenging. What base languages are we using? Well, all of the APIs we're considering are loosely sort of extensions of standard language, C, C++, or Fortran. That's quite typical in HPC. OpenMP extends C, C++, or Fortran. MPI is callable from C, C++, or Fortran. Some of them support all the base languages. Some only support C++. And also, you have to be careful that the API may not support the most recent version of the language. So if you're a very keen C++ program who wants to use very, very modern C++ features, you have to be careful because you need to check whether the GPU API supports these as well. Because remember, the compilers for the CPU are typically maintained by large communities of people, very up to date and very modern. There's much less community support for the GPU sections of the compiler. So the compiler which produces the GPU code may have fewer features, and we've seen that as an issue in C++, but also in Fortran. If you're a very modern Fortran program, you like to use really, really modern Fortran features, then that can be an issue in taking the code and running it on the GPU. Portability is an issue. I mean, it maybe wasn't so much of an issue 5 years ago when the GPU market was completely dominated by one manufacturer, NVIDIA. There is competition coming up, and actually on ARCHER2, one of the interesting things about ARCHER2 is it isn't NVIDIA. They are AMD GPUs, and Intel have a GPU product in the pipeline. So portability across GPU hardware platforms is really a serious consideration. You don't want to develop a program which only runs on NVIDIA or AMD GPUs, because the next system you have access to may not have that particular architecture. Now, portability can mean two things. In HPC, clearly there's does the code compile and run, but also does it run? Is the performance portable? Does it run efficiently? That's another question. It would be nice to have the same code to work on both CPUs and GPUs. That is really quite tricky to do in practice. And again, performance portability is an even bigger problem here. It can be very, very difficult to have a single code base which both runs on the CPU and the GPU and runs efficiently, because what you'll see later on that, for example, very basic things like the choice of data layout, which do your arrays go IJK or KJI, can be different. You might want to use a different data layout for your CPU and your GPU code, so that can be an issue. But portability is a serious problem, a serious thing to consider. Also, a lot of us, you don't write just base code. If you want to do a Fourier transform, you call a library. If you want to do matrix operations, you call BLAS or LAPACK. And so, access to numerical libraries on the GPU could be very useful. Differ in their support for this, but some APIs are interoperable with each other. So, for example, you could have OpenMP interact with CUDA, which is the NVIDIA directives-based language. So they have a BLAS library for the GPU called CU BLAS, and with OpenMP there is the interoperability between those two standards is defined. So we have open and proprietary specifications. Open specifications are maintained by the community, and these are things from the HPC context like OpenMP and NPI. They're more likely to be portable across hardware platforms. They're more likely to be supported by a sound process, that the features are proposed and then evaluated and implemented if they're seen as being valuable. And they're more likely to survive, manufacturers coming and going. And also there's really in the community, for a community maintained specification, there's a lot of pressure and community pressure to have backwards compatibility. You don't want to say, here's the new version, it's not compatible with the old version. However, because they're portable, they're less likely to exploit vendor-specific hardware features, and they're less likely to react quickly to support for new base language features. So the fact that they are maintained by consensus and by committees and such like means they don't move quite so quickly. And so I'm going to basically use a very, very simple example as a way of illustrating how the GPU programming models work. And it's called SAXPY. It's a vector-vector operation. It stands for a single precision, SAX plus Y is a standard BLAS termination, single precision alpha X plus Y. So what you're doing is you're doing a vector operation. This would be the CPU code. Y is AX plus Y. You're doing a standard linear algebra, adding one vector to another with some scalar multiplier. If you wanted to do that on a CPU, you'd write this code here, or in Fortran, you'd do this. So you have a vector of length n, and we're doing single precision here for the sake of argument. Y is AX plus Y. And you might do that, or if you're a Fortran programmer, you might do it in array syntax. If you're a C programmer, C++ programmer, you might call a BLAS library to do that. And the standard function in the BLAS library is called SAXPY. So how are we going to do that? And we're going to use this. I mean, there's not enough time to go through exactly how each of the models work here, but hopefully by showing you example code which implements this, you'll see in principle how they work. And I have provided specific examples for OpenMP and CUDA and HIP. Apologies, HIP. We'll talk about that later. This is the example we'll use just to check you can all get logged in and compile and run. So the CUDA programming style is explicit kernels. It's callable in C, C++. There is some support. There is a version called CUDA Fortran, but it's not so well supported. This is NVIDIA's kernel style programming API. The one we'll see, which is available from AMD, their kernel style programming language called HIP, and it's very, very similar. So actually you can semi-automatically translate. So although CUDA is NVIDIA specific. If you write a CUDA program, it's pretty straightforward to convert it to run on AMD via HIP. The base languages were C originally. Now we have C++ and CUDA Fortran. CUDA Fortran is actually a language extension to Fortran. The library support is quite good. There are lots and lots of libraries have been implemented to run both on the CPU, and NVIDIA have provided CUDA versions for the CPU, or other people have done it. We said CUDA interoperates with OpenMP, also interoperates with OpenACC, which is another directive-based approach, which we'll cover later on. So the downside is it's proprietary to NVIDIA. They just decide what is going to be in CUDA or what isn't. And there is an API for NVIDIA hardware, which is called HIP. So how does this work? Well, the way it works is if you were to run the SAXP example in CUDA, the first thing you do is you write a function, okay, SAXP, which does the operation you want. So you have a SAXP function which takes a size and an A and two arrays X and Y. And what you want to do is Y is AX plus Y. Okay? So you write something which looks a bit like a normal function. However, there's two things which are different here. Well, first of all, you have to annotate it saying I want this to run on the GPU. So there's this strange precursor here, _global, which tells the compiler this is something I want to run on the GPU. This is a kernel function, so please compile it to the GPU. That's one thing. Secondly, you'll see there is no loop in here. As I said, the way kernels work is you write a single function. There is some syntax for executing it across all the GPU threads at once. So within this function, there is a way of working out which GPU thread am I on. So this gives you an index I, which tells you what is my, in OpenMP, it's sort of like your OMP get thread num. Although you have to realize here that there will be many, many thousands of these, not a few tens as there would be in OpenMP. But what you do is you have a function. Within the function, you say which thread am I running on? Thread I here, which is like OMP get, whoops, sorry, OMP get thread num, and then you execute Y as A to AXI times Y. You have to also check that you're not out of range. Okay, so you'll see here there's a bit of boilerplate you have to do, and then the code you write on the CPU side. So this executes on the GPU. The host code which runs on the CPU, you have to allocate the data for the on the GPU, and there's a CUDA malloc here. You have to then copy from the host on the CPU to the device. You copy from your X and Y arrays on the CPU to the versions on the GPU. And you then have this slightly strange syntax which says SAXP, and this triple chevron here basically says I want this to execute this kernel code on the GPU. And you give it the normal parameters N, A, X, and Y, but this syntax here executes it on the GPU, and these strange parameters here give you control over how many. This is saying please implement this in blocks of 256 threads. We'll come back to what this means, and this is saying this is how many blocks I want. So there's quite a bit going on here. But this is effectively the way you allocate the memory on the GPU. You explicitly copy from CPU to GPU, and you have this CUDA-specific syntax for saying, please execute this kernel, this one here, across all the threads. And this is a way of distributing it across the threads, launching some control over how the threads are launched. And we'll come back to what that means, how that relates to the GPU architecture later on. But the important point here is you have code which runs on the CPU, code which runs on the GPU. There's no explicit loop. The loop is implicit, and this is the magic code which does that, launches the kernels across all the GPU threads. HIP is very like CUDA. It's kernels. Its the portability is to AMD, but actually they have a translating program called Hipify, which can translate NVIDIA CUDA to HIP. The base language is C++. There is some support for Fortran, but really it's a C++ interface. The library support isn't quite so good as CUDA because HIP isn't hasn't been around for longer, and AMD GPUs are newer than CUDA GPU, than NVIDIA GPUs. So the NVIDIA ecosystem tends to be more mature. It is proprietary to AMD, but basically it directly shadows CUDA. So not all the latest CUDA features may be available, but it really shadows CUDA. And so if we look at the HIP code was OpenACC. In fact, basically you could replace HIP with CUDA here, or CUDA with HIP, and this gives you exactly the same thing. So this is really line for line identical to the previous CUDA code, with CUDA replaced by HIP. OpenCL is a kernel style, but it's been around for a long time, and it was really developed to run code also on CPUs, and it's portable to AMD, NVIDIA, and Intel. It only supports C. There's lots of library support, and the specification is an open one. There's a group called the Kronos group that supports it. It is designed to be portable across CPUs and GPUs, but the performance is kind of difficult. The kernels are compiled just in time, and it really is very, very low level. Okay, so you'll see that in the CUDA HIP examples, there is a bit of setup to do. We have to allocate the memory and copy it, but this isn't massively different from the serial code. It's kind of sight read it. I'm not going to go through the OpenCL code. Well, I'll show it to you, but you will see that there is, and a lot of this is boilerplate. But OpenCL is typically not very widely used in the HPC community because of the amount of setup you have to do. And I'll go through the code. Here we go. I'm not going to go through this, but you'll see there is an awful lot of boilerplate code to go through here. Now, of course, you could wrap this up in macros and such like, but there is a lot of stuff to do. And you'll see that so the kernel you write for OpenCL is very, very similar to the kernel you write for any of these kernel-based approaches. It's basically, you say, I want to get, I have a function. Within that function, I get what my thread ID is, and I execute the code on, I don't have a loop, I execute it on only one of the indices. Y of my thread ID is 8. And the distribution across threads, the loop is sort of implicit, but the amount of setup here is quite staggering. So I won't go through that. SYCL is sort of a kernel style, but actually it's sort of halfway between a kernels and a new sort of language type support. It's portable to AMD, NVIDIA, and Intel. It only uses C++. The library support isn't so huge. It's again open administered by something called the Kronos group, and it's a very high level interface. And it's very integrated with C++. You have C++ lambdas replace the kernels. It will look, if you're a C++ programmer, it will look quite natural, but it's relatively immature. There's not so many implementations. Again, it can generate CPU code, but it's not as abstract as the portability framework. So it sits somewhere between the kernels and the portability frameworks. And the way it works for SAXPY is that you declare some buffers, which are like the GPU memory, which are SYCL buffers, and then you have some statement which basically says, I want to execute this function, which is this, across a whole bunch of threads. So to me, as not a C++ programmer, this looks rather unintelligible. If you're a C++ programmer, possibly this looks quite natural. But that's the way it works. It's kind of a kernel's approach. You write something which operates on a single index I, and there's some syntax for launching this in parallel across all the threads of the GPU. OpenMP offloading, which is what we're going to concentrate on in the course, is a directives approach. It's portable. OpenMP is a portable standard to CPUs and GPUs, C++ from Fortran. There's not so much library support, but it is interoperable with CUDA libraries. So if you wanted to have an OpenMP program, but call a a CUDA-based FFT, you could do that. It's open, it's administrated by the OpenMP Architecture Review Board. It's relatively mature. It is in principle designed for devices other than the GPUs. So you may look a bit quirky and a bit verbose in places. Its major use is for offloading to GPUs, but in principle, it's designed for more than that. But that's one of the standards we're going to be concentrating on. And you'll see again, if you're a CPU OpenMP program, this looks much more familiar. We have a loop, explicit loop, which is just the one we'd have written in our normal language, and we have a hash pragma or an OMP directive, which says, I want you to distribute this in parallel. And you'll see here, we want to copy the data. We're copying Y in from the CPU to the GPU, and we're bringing back, we're copying Y in and out, and we're copying the X and the A in. So these are, this will look, you won't recognize some of these clauses if you're a CPU OpenMP programmer, but this looks like, copy in, copy out, OMP parallel forward. It looks similar. And you'll see it's like one extra line in C or in Fortran to parallelize the loop. There's another style called OpenACC. It's a directives-based programming style which predates OpenMP. It's maybe 10 years old now. And it's very similar to OpenMP, but OpenMP is kind of caught up. So OpenACC predates OpenMP, but it has fewer implementations because people are now focusing on OpenMP. So a lot of the development and investigation of how to do directives-based offloading was done in OpenACC, but nowadays you probably would recommend using OpenMP over OpenACC. We will cover OpenACC in this course because you may come across codes that use it, but OpenMP has they're pretty similar functionality, and OpenMP is more modern, more widely available. So the OpenACC PSACSP looks very similar. You have an explicit loop, and you parallelize it with copy in, copy out data from CPU to GPU and back, and you tell it it's a parallel loop. CoCos is one of these portability frameworks. It's based on C++. It's maintained by a bunch of US labs. And again, it's designed to implement code for CPUs and GPUs and may generate CUDA, HIP, OpenMP, or whatever, even in C++ threads. So we're not going to cover that in detail here, but I'll show you what does the CoCos code look like. Well, it's really quite compact. You basically have a new language extension which says you have a parallel for. So you just basically say, I want to take this loop and I want to execute it in parallel. So it looks, it's very high level, looks quite easy to write, but as we've said, there may be concerns about getting portability. Raj is another portability framework based on C++. It really comes out large level, more laboratories, so it's kind of a bit more of an informal standard. Again, it has the same aim as CoCos, generate efficient code for CPUs and GPUs, but it does have level APIs, but in principle, it's very similar. You write your loop, and you have some new syntax for launching that across the GPU threads. So, summary: there's a wide range of programming models available for GPUs. This course will focus on OpenMP. Well, I say actually, we'll cover OpenACC as well. This course will focus on directives. We'll do OpenMP first. We'll also talk a bit about OpenACC. The reason we're doing that here is they're portable to different architectures and extends the well-established OpenMP approach. I've seen most of you know OpenMP for the CPU. Hopefully, OpenMP for the GPU will be a natural next step. The exercise will be done on the ARCHER2 GPUs, which is an AMD architecture, but it should be very straightforward to port, for example, to NVIDIA GPUs. And there's some references here you might look, so I'm going to leave them up. So are there any questions about that? I take the same runtime with the GPU. Yes. So the runtime will, yes. So the, for example, in CUDA and HIP, you specify a kernel, and you say please execute this kernel in parallel across the CPU or across the GPU. But how that is done is opaque to you. Yeah, that will be, you know, the AMD will have written a runtime for doing scheduling that and running those threads, and NVIDIA will have written one for doing that for their GPUs. So yes, you have to basically, yeah, you don't have any control over that. I don't know what's your most, I mean, I suspect it's CUDA. I suspect because, you know, until recently, till a few years ago, NVIDIA were the only people who produced GPUs which were usable for HPC. The only real way for programming was CUDA. So I suspect CUDA will be most used, but going forward, you know, you would probably want to move to a more portable framework. And that's just a guess. I don't actually know, but I suspect, you know, if you've got a fully functioning GPU code just now, you'll have to be working on it for a long time. When you started, probably CUDA was the only option. That's my guess. So sorry, no. So I mean, you can learn about the architectures and the way that GPUs work, but if you only know, do you know C? Sorry, do you know C? So you don't know C++, but do you know C? Okay, no. So this course really focuses on compiled languages. This is for Python, but they're much higher level. So for example, if you were doing machine learning, you'd do something, or after you'd use something like PyTorch, which would run stuff on the GPU, but that would just be, you know, please do this, you know, please train my neural network and do it on the GPU, and that's way down below. So, you know, in terms of I mean, I think you might find it interesting, but and definitely the GPU architecture course. So the general comments about how GPUs work and such like are relevant to any language, but the specifics of how you actually, we will only be covering compiled languages here, C, C++, and Fortran. So maybe the first day might be interesting, but I think the later ones possibly not. So sorry about that. I don't know about SYCL. I mean, I've only written very simple SYCL programs. I mean, in principle, there's for it to be any slower than OpenMP, but there was a lot less support for it. You know, the nice thing about OpenMP is a lot of industry and community support for it. So I suspect that my colleague Mark, who will be lecturing later, has a lot more experience with SYCL. So, you know, it's a very different model. It's like a kernel's model. It's really suck it and see. Unfortunately, you'll have to try. I suspect it won't be as good as OpenMP because there is more. Currently, there's more traction behind OpenMP. My understanding of the SYCL model, I may be wrong. My understanding was it was developed very early on to allow people to develop games and write games portably across different GPUs. That, I believe, that was its original, and then it was realized that that model actually worked to general HPC programming. But we have had SYCL courses, but I don't know. I would suspect you know, that I wouldn't expect it to be more performant than OpenMP, but I don't know if it's slower in practice. Okay, so what I'm going to do now is, I think I'll just, that I will, I'll take a 5-minute break to get some water. At 10:55, I will go through the practicals. I'll go through logging on and running simple. I'm typing something in here, but so. And then the next lecture will be at, we'll say in half an hour at 11:20. So that's, I will now so hopefully that's I'll move that about. I'll go through that, and then so if you're interested in the practicals, you might want to come back in 5 minutes, and I'll go through how they work and such like, get you logged on. That might take 10-15 minutes, but I'll give a half an hour, and the next lecture will be 11:20, and we'll aim to finish for midday. Okay, so okay, hello everyone. So what I was going to do is basically just take you through logging in and getting some simple programs running. So I will show you, for example, where the sheet is. So if we go to this is the web. This is the page you should be on. If you go into exercises, now this is quite. Hopefully there aren't any bugs in this, but I only did this quite recently. But the Saxby tells you how to get logged on and such like. So hopefully you have access to that, which just goes through what we need to do. But I will open that up myself. Okay, so now, oops, I've got too many windows here. I will now share a window which is okay. So first of all, I have to log into ARCHER2, and that's what you need to log into. Now, hopefully, this requires you to set up a number of things, which are an SSH key pair and multi-factor authentication. I've already logged on today already just to check things are working, so I will not get prompted, but that you should be able to. So I'm just, I don't know how many people are actually interested in the practicals, but I can actually, I don't know if people are able to log on. So I can see that, someone with a very, very similar login name to me, TA Hunt1, as opposed to TA Hent1 is logged on. That you may be logged on a different login though, so I don't know. I just wanted to check if there's somebody working along. If you're okay, fine. Okay, that's good. Right, that's brilliant. There's a few people. If you have any questions, please. So what we need to next do is we do need to see. You need to agree in the work directory if you've not used Archer before. So you need to do cd/work/TA200/TA200 and then your username, which for me is, this is not my TA200 Hent1. Okay. So. Okay, so Uraj, so one of the reasons I wanted to do this session was so that you had time before. So that's explained on. You need to do that from safe. So we can maybe look at that later on. There probably isn't time just to sort that. It's not complicated. Maybe not time to sort that right now, but we can maybe do it at the end. I can show you how to do it at the end, or it's on the web page. So it's a fairly standard TOTP. You need to do it via the safe. There, you need to set an MFA token via the safe. But that's why I want to do this now, to sort these issues out. Okay, so I would maybe do the git clone. So let's clone the repo. And then we go into that directory. And we also want to go to this. We want to go to this current git checkout 2025-04-22. So that should then get you. It's a bit slow, but it is working. Yeah, there seems to be a bit of a delay. I don't know what happened there. Jonathan, is that network or just okay, fine. So there's plenty. So now you'll see that that I also say that they're available in for various reasons. Oops, sorry. This is new. I haven't managed to get into that yet. So for the moment, hopefully that will appear there later. For the moment, it's actually here. So I'd recommend you to actually just check out the repo. If you do want to just copy directly on ARCHER2, by the end of today, my file will be there. But at the moment, it's not there. Sorry, that was my mistake in setting this up too late. I saw there was a comment there. Okay, fine. Okay, I don't think I missed anything. Okay, so again, the exercise we're going to use is the Saxby one. Sorry, we're going to exercises. Sorry, so I did. We need to go to exercises. I didn't put that in. And we unpack it. Saxby.tar, and we go into Saxby. So I have two versions here, a HIP version and an OpenMP version. And I'll just show you what the HIP version looks like, for example. This is actually the code, actually cut and paste directly from the slides, but we'll see that there's a bit more boilerplate here. But it is exactly the code. There's some setup, but this is the code directly from the lecture. But there's some setup here where I just allocate the X and Y. I initialize them to some known values, and there's also some. I do a checksum. Okay, but hopefully that that shows you this is, and at the bottom will be the kernel code. Okay, here we have. Okay, this is from the. So this is exactly the code from the lectures, except I've got a bit of setup, mallocing and initialize them and such like. Okay. So hopefully that looks fine. I should then be able to compile. Now you need to load some new modules, because so we need to do module load progenv AMD module load ROCm. That's the sort of HIP support module load Cray P Excel AMD just GFX90A and module load Cray P-X86-Milan. There we go. Fine. So having done that, we can now compile the code make-f makefile HIP, and that runs the HIP compiler, which is called HIPCC. So that's compiled the program. But now we want to run it. Of course, we can't run it on the CPU. Well, actually, what happens if I try and run it? Never tried that before. Let's try HIP Saxby. So that has, well, it got the wrong answer. So I didn't think it would run, actually. Didn't think it would run. But what's happened is that it hasn't done the right. So I suspect that the calculation, I suspect the offload the instruction which says please offload this to the GPU has just been ignored, and that's why the answer is wrong. That's interesting, actually. However, we want to run this on the GPU, and to do that, we need to submit it via Slurm. So I've given you a Slurm script, hipsaxby.slurm, which has the magic in it, which says I want to run on one GPU on the GPU partition. This is just, and I just run it. So this is, I mean, this is just standard. Well, this is just a way to run stuff in the batch system. There's various setup you have to do. I've given you a pre-packaged script to do that. So what we do is sbatch hip-saxby, whoops, hip-saxby.slurm. It's running, SQ-B, so showing my jobs. It's completing, that's CG means completing, and it's finished. So if I look, there is now a file called hip-saxby.out, and if I look at that, whoops, hip-saxby, you'll see that, yeah, so hip-saxby then equals 1,000,000. The checksum, I know what the answer should be because it's just integers, I had them up. The reference, okay, so this is the answer I get, this is what I should get, they're the same. So that's good, that as well. That's interesting, actually. I'm glad I put that checksum in. I wondered, is it worth checking the calculation is correct? And you'll see that when we run the CPU, we can see it's getting the wrong answer, which is interesting. For the OpenMP version, sorry, OMP saxby.c, you'll see that this is very much the same code. I've got the setup, the same setup here, but the offload is exactly the code from the from the slides. Have only typed to power of 4. So if I make that, it uses the standard C compiler with the -f OpenMP as you'd expect. But here the directives are different. How did it know to generate for the GPU? Well, those directives are explicitly GPU directives. I'm now going to run this on the front end because I don't know what's going to happen here. Okay, there we are. So this is basically saying this just ran on the CPU. So the OpenMP says, look, warning, runtime do not match any image. So it's saying you wanted to run on the GPU, I couldn't find one. So it just ran it in serial, I guess. I don't know exactly what it did, but it got the right answer. But it's actually telling you this is not running on the GPU. You wanted it to run on the GPU, I can't. So it seems to be just reverting to running on the CPU. However, if I sbatch the OMP saxby.slurm, it's pending, it's running, it's completing, it's still completing, it's finished. And then we'll see the same thing. Yeah, it now there's no complaints, so it is running on the GPU, and we get the right answer. Checksum is this, and the reference is now. So hopefully that, again, the only reason for this exercise is just to give people a chance to log on, compile, and run real programs. I don't know, has anyone, now I saw that Urge had a problem. We can sort that out later, but does anyone, has anyone great, so I haven't messed this up completely. Good, that's really good. Yeah, good, that's good. Yeah, so fine. So hopefully that's given you, so after the next session there will be more realistic examples where you have to compile and run your own code and things, but hopefully this gives you a template. I mean, there will be templates. I wanted to check now that it was all working okay. So as I said, the model for this course is that you do the exercises in between the lectures, but obviously there's a chance during the lectures or after them to sort out problems, ask questions. So that's gone surprisingly well. So as I said, I will now yeah, so that's it. So the next lecture at 11:20. So I'll take a 10-minute break and see you all again in 10 minutes for the final lecture. But I'm glad that people were able to run. Okay, so I'll give the final lecture today, which is about GPU architectures. I think there's two things to consider here. One is what the architecture of a GPU, and it is very different. Well, it is different in many ways from a CPU. But secondly, it's maybe been implicit in what I said in the first lecture, the way that you use GPUs, you actually run a program on a CPU and then you offload to the GPU. So how did the CPU and the GPU fit together? So again, please ask questions as we go along. So a very simple model of performance for any computer is you have a processor, a CPU or a GPU, and you have memory, and you take data in and you get data out, input and output. And that is, clearly a very simple model. But for HPC, I think it's very important to realize that for large-scale computing, in fact, the bottleneck is often the data transfer. The bottleneck is not often how quick your processor can work, but how fast you can get data in and out. Quite a long time ago, people who were developing games for 3D games consoles and such like, started to develop their own processors, graphics processors, which were designed for doing graphics operations, doing 3D rendering of scenes, but also a graphics processor has to process a lot of data, and so they actually addressed the problem of this data bottleneck. So graphics processors were originally designed to do graphics, to play games, do visualizations, but also to have very, very fast bandwidth to memory. And that's what made them attractive for HPC, the fact that they had very fast memory bandwidth. So there's a lot of factors affect the performance of any processor. The clock speed, the rate of issue instructions by the processor. So a modern CPU has clock speeds in the gigahertz. When you load data from memory, there's two things to worry about. One is the latency. How long does it take you to receive a data? You request some data from memory. You want to load an 8-byte double precision number. How long does that take? But also, once you started to access it, how quickly can you get it in? How many gigabytes per second can you transfer? And of course, parallelism can replicate the basic processing unit. So we know in modern CPUs, a processor can have on your laptop maybe 8 CPU cores, which are effectively independent processors. On a high-end system like ARCHER2, there may be 100 CPU cores attached to the same memory. So the important, you may have seen this kind of graph before, but for at least 4 decades, from the 1970s all the way through to maybe 3 decades until about the early 2000s, the way that you got increased performance for your computer was the clock speed went faster. So the frequency was megahertz back in the 70s, up to gigahertz and multi-gigahertz in the early 2000s. But then that has just plateaued. Okay, so an individual process has not got any faster for the past 20 years, and that's really due to power limits. At this speeds in the gigahertz range, it takes an enormous amount of power to drive that speed of processing, and basically processors would get too hot. You could run processors faster, but they get way too hot. You couldn't have them in a laptop because you couldn't cool the laptop; it would burn your legs. You can't have them in a large HPC system because the power consumption would be far too high, and you couldn't afford it. So how have computers got faster in the past 20 years? Well, they've got faster because although an individual processor hasn't got any faster, a modern processor has many CPU cores on it. So back in the early 2000s, a typical CPU might have 1 core. Now we have many tens, if not hundreds of cores on a single CPU. But the actual frequency has plateaued at a few gigahertz for the past 20 years. What about memory? Well, unfortunately, memory hasn't really got much faster. Retrieving data from memory can take 100 or 1,000 clock cycles, which is a long time. Now, if you look at those figures, you would say, well, that means that your laptop will run at a snail's pace. Of course, it doesn't, because what actually you do is when you load data from memory, you don't load it from memory. The processor goes to great lengths to try and make sure that it's in cache. So we have a lot of levels of cache to reduce that, but it is important to realize that accessing memory is very slow. The bandwidth, well, we have a order 100 gigabytes of memory. On ARCHER2, we have 200 or 500 gigabytes of memory. The bandwidth is maybe a few hundred gigabytes per second. That may sound like quite a lot, but that's the you can transfer data from your CPU to the memory at maybe a few hundred gigabytes per second. But remember, the processor can have hundreds of CPU cores. The actual bandwidth to a single CPU core might be in a few gigabytes per second, because they're all sharing this bandwidth. So this figure isn't as high as you might think, because this bandwidth is shared amongst all the CPU cores on a processor, which can now be many tens of them. And in HPC codes, the bandwidth to memory is very, very often the bottleneck. So what we've done is that we to make things faster, we use CPU parallelism. We can't make a single CPU core go faster, we use lots of them. And so there's two ways we do that. We can have multi-core systems, so a modern CPU has many cores on it, but we can also parallelize, and MPI allows you to parallelize across multiple CPUs as well. But to get increased performance, the only way to get increased performance nowadays is, because the speed of an individual core is limited or capped, we have to go multi-core or go parallel. Now, what GPUs do? Well, a modern CPU are incredibly complicated. So you have some memory, you have a lot of cache, because we've seen access to memory is very slow. We have to cache things. You have your ALUs, your arithmetic logic units, which can do add, subtracts, and multiplies and such like. But there's a huge amount of control area. So a GPU has a lot of space dedicated to caching, but also to controlling. A modern CPU is incredibly complicated, and there's an awful lot of control goes on to allow these things to do complicated things. We'll see on the next slide what they are. A GPU is much simpler. It has high bandwidth memory. We'll see how fast that is later. But locally, they have a lot less cache and a lot less control. They're very, very simple. So rather than having a small number of order 10, very, very complicated and general purpose logic units, things which do the processing, we have a much larger number, we'll see hundreds or even thousands of very, very simple things. And the history of this is that these GPUs were built to do one thing, which is to do graphics. And the number of operations you have to do graphics is relatively limited. So that's whereas your CPU is designed to do everything. Okay, log you onto Facebook and run a browser and such like. So that's the way they work. A lot more of the physical area, a lot more of your transistors are dedicated to actually doing hardcore floating point computations. So the CPU computation is a bigger, much more general purpose, but smaller in number. The CPU cores are much faster, they have a much higher clock frequency, and they're much smarter. And a modern CPU can do an awful lot of clever things at runtime. They can do out-of-order execution, they can do speculative execution. They will say that there's an if statement here coming up. I don't know if the if statement is going to be true or false. I'll execute both of them just in case and roll back. They do a lot of incredibly complicated things for very general purpose computation. But GPUs specialize in floating point operations. Multiply, add, fuse, multiply, add, and now they have special cores for doing small matrix operations. They call them tensor cores. They even have hardware support for things like ray tracing you might want in high-end games. But they're very much more specialized. So the actual clock frequency is much lower, but the performance of a GPU doesn't come from the processing capability of individual cores. They're much simpler and and actually slower than on the CPU. It's the massive parallelism. So although parallelism is very important in CPU programming, it's absolutely fundamental to GPU programming. Unless your program is parallel, there is no point using a GPU, because the performance of a single core is terrible. But there are many, many thousands of them, so the performance of a whole GPU is very good. So also GPUs have high bandwidth memory, but they also have high latency. And the way that a CPU hides the latency is through caching. So, you know, the first time you access some data from memory, it may take a long time, but the next time you access it, you hope it's still in cache. Okay? What GPUs do is something very, very different. And actually, it took me a while to get my head around this because as a CPU program, it's not obvious. They have multiple threads. So basically, you run many more software threads than physical cores. Now, on a CPU, if you're an OpenMP program for the CPU, you have 32 physical cores. I'll run 32 OpenMP threads because if I run more threads than physical cores, the overhead of switching them, context switching, descheduling and rescheduling the threads to the physical CPU cores is so high, my performance is terrible. GPUs are designed to run more software threads than physical cores. The reason being that whenever it's one stall, so you request some data from memory, the GPU notices, okay, that bunch of 128 threads or whatever have requested data from memory. That data is not available yet. Rather than waiting and stalling, it says, okay, I'll park them and do something else. So you want to overload the GPU with many more threads than physical cores, so that when one set of threads stalls, another set can be switched back in, and they can be switched back in, I think, almost a cycle. The context switching is almost instantaneous. So as soon as a bunch of threads stalls on a load from memory, the GPU can say, right, I'll run these other threads who maybe now have their memory available, have the data loaded. And so it's a very, very different model based on very, very fast context switching of the threads, the software threads onto and on or off the physical cores. It's exactly what you don't do on CPUs. On CPUs, you do not want to context switch. You want to have the same or fewer software threads than physical cores. The other important point that GPUs use is SIMD, single instruction, multiple data. All the GPU cores in bunches of, say, 32 or 64 come back, but operate the same operation over different data. So this is very like vectorization. Okay, modern CPUs support vectorization, or vector instructions, and so the CPU may be able to say, rather than add this data to that data, it may be able to say, add these 4 data items to these 4 data items. It has a vector instruction which does an addition or multiplication on 4 or maybe even 8 elements at once. This is fundamental to GPUs, that the GPU cores are designed to execute exactly the same operation, but over different data. And so this concept of vectorization or SIMD is actually absolutely crucial to GPU operation. So rather than n clock steps to process n data points, n compute to process n data points in a single clock step. So you say, you have, and it will turn out to be a bunch of, say, 32 or 64 threads will operate at the same time, but on different data. And the SIMD model is very effective. It's clear it's very, very effective for computer graphics. That's why GPUs use it. You're basically having the same operations on thousands or millions of pixels in an image. Also highly used in AI models. You can have you're doing the same operation on different input data sets. But of course, we use it in scientific simulation. Okay? If you're doing a simulation of the weather, you're doing the same calculation effectively over the whole of the UK to produce the weather tomorrow, but each calculation, each grid point has different data. So SIMD is a quite an old concept. You might call it vectorization, but it's fundamental to GPUs, how they operate. So this is a picture of and I'm not really a hardware person, but this is a picture of an NVIDIA A100 relatively modern GPU, and what you can see here is that this is called a GPU processing cluster, but within that we have a streaming multiprocessor, an SM. So this is like a streaming multiprocessor is like a single compute unit. Sorry, that's the wrong terminology. It's like a processor, but it has multiple threads in it. Okay, so that's a streaming multiprocessor. There's also text. There's other stuff here. Actually, I've got the wrong way. Text to multiprocessor. This thing here, but this is your streaming multiprocessor. This is like your GPU processor. There are lots of them, but even within this is multi-threaded. Okay, within that. And so you can see the cache. This is like a physical picture, a relatively good diagram. The cache takes up relatively small amount of space. Almost all the space is generated to things which actually do floating point calculations. Each SM is actually divided into sub-blocks, but each of those blocks has lots of very simple floating point or integer units. So it has a lot of these very simple units for doing 64-bit or 32-bit or 32-bit integer operations. Modern GPUs can even do reduced precision. They also now have these tensor cores, which is designed for doing, I believe, very fast 4x4 matrix operations, because graphics is based on rotations and scaling. A typical graphics transformation is represented as I believe, as a 4x4 matrix corresponding to rotation in 3D and some kind of translation. I'm not an expert, but that's how a GPU looks. The AMD one's very similar, but AMD use different terminology. Yeah, so tensor cores for matrix operations. I believe it's for 4x4 matrix operations. I'm not an expert, but I believe that's its fundamental target, and that's because graphics processing uses 4x4 matrices. See, the AMD structure is similar. They use different terminology. They have a compute. So compute unit is the equivalent of a SM. So NVIDIA talks about SM streaming multiprocessors, and AMD talk about compute units, CUs. Okay, so that's so it's SM for NVIDIA means compute unit CU, which is like the smallest GPU processor, but it is internally multi-threaded, which is the main thing to realize. So on ARCHER2, now ARCHER2, the GPUs on ARCHER2 are very much for development. We only have ARCHER2 is basically a large CPU platform with 750,000 CPU cores, but as a development, and we have these 4 compute nodes. Each of them has 4 of these MI210 GPUs, and each one has 104 compute units and 6 GB of memory. And as we said, the way a GPU works is that you run your program on a host CPU and offload instructions to the GPU. And so the reason why I have to do quite a few different module loads on ARCHER2 is the CPU for the GPU nodes is different from the CPU from the main computational units. It's a 32-core Milan CPU. And this illustrates the architecture that you run your program on the CPU. It's offloaded to the GPU, but currently on sort of standard current GPUs, that is done through a PCI Express bus, and this is really quite slow. So the bandwidth between CPU and GPU is really not very good on sort of current or previous generation systems. So that is a major bottleneck. But that's what it, so there are actually 4 GPUs on a node hosted by a single 32-core CPU. We are actually running programs, I believe, on single GPUs. But the fundamental the concept, I said that each of these CPU multiprocessors or compute units was multi-threaded. Blocks, and the way that that GPU programming works is that your threads are packaged together into what NVIDIA calls blocks or AMD calls work groups. These are collections of threads. And these work groups are assigned to the SMs or the CUs, but fundamentally within that, they execute in SIMD, 32-way SIMD on NVIDIA or 64-way SIMD on AMD. So fundamentally, at any one time, all 32 or 64 threads have to be doing the same thing. Okay, and that's the only way you get performance on the GPUs. You can arrange for calculation to be dispatched in large blocks of, say, 32 or 64 threads. NVIDIA calls them warps, and AMD calls them wavefronts. You could just think of them as SIMD instructions if you want, and they have to do the same thing. Now, if they don't do the same thing, it will be it will be serialized. So, well, not serialized, but for example, everything is done in blocks for 32 or 64. If only half of those threads are operational due to some if statement, then they'll all operate, but half of the results will be thrown away unmasked. So fundamentally, you're running 32 or 64 threads simultaneously at any one time, and your job is to make sure that all those threads are doing useful work all the time. Otherwise, your program will not run fast. And I said these are called warps or wavefronts in NVIDIA or AMD speak. The memory hierarchy is also important. So we have these streaming multiprocessors in NVIDIA. There are registers, so each thread has its own registers like a normal CPU. Not a huge number, but it has some registers. And so each thread has access to a fixed number of registers. I don't know how many it is, but it's just the same as a CPU. If you do require more registers, it will spill them over into the global memory as a scratch, but you really don't want to. You want to try and each thread does have access to a set of registers, just like a normal CPU. There is an L1 cache here, which is shared amongst a single streaming multiprocessor or compute unit. And so caching is done on a per SM basis. There is shared memory, which is shared between threads in the same block or work group. So we have shared memory and registers on each SM. There is something called, there is read-only memory as well. This comes from graphics texture mapping. If you wanted to texture a surface to make it look like grass or something, you would load in some texture and then apply it across. So this used to be called texture memory, but it's a set of read-only memory which can also be used. So the read-only memory has, there is some read-only memory which could be used for texture, a bunch of different things. So there's lots of times you want things to be read-only for just instructions, for example. And in graphics, it would be texture memory. But in CPU, in an HPC concept, it might be for constants. It might be stored in the read-only memory. There is a level 2 cache that's shared globally across the entire, all the SMs and compute units share the level 2 cache, and it's basically the same as a CPU cache. It manages and stores frequently accessed data from the global memory. But you can see it's not really that big. You have many tens of gigabytes of main memory, but only a few tens of megabytes of cache shared amongst many SMs, each of which has many threads. So there is also global memory, which you think of as just normal memory. It's accessible by all threads, but access is relatively slow. So your data, is stored in the global memory, which is tens of gigabytes. But hopefully, you hope that when you access it, it's in the cache or stored locally on the SM. So this is a very useful, I mean, that was really very detailed, but this is a very, very useful conceptual diagram of how a kind of modern standard GPU system works. On the host side, the CPU side, you have a standard CPU that has order 10 cores. We saw 32 on ARCHER2. It has a few hundred gigabytes of memory, and the access time between the CPU and the GPU is maybe of the order of a few hundred gigabytes per second. On the GPU side, we see we have many more cores, thousands of hardware threads. We have a large amount of, we don't have maybe have so much memory. The memory is very expensive, so maybe tens of gigabytes of memory rather than hundreds, but the access speed is very fast. So we have thousands of gigabytes per second transfer between the GPU and the high bandwidth memory. And so that is very, very fast. The problem is that we have to offload. The model is that you run your program on the CPU and you offload data and calculations to the GPU. On standard modern systems like ARCHER2, that interface goes across, that link is through something like PCI Express, which is very slow. So that the bottleneck in this system, is transferring data from the CPU to the GPU, and therefore the art of GPU programming is to transfer data as little as possible. Okay, transfer it once at the start, do all the calculation here and then back again, not transferring every iteration. Now that is because CPUs and GPUs were developed independently. CPUs for your laptop, GPU for your gamer's machine, and they're kind of just bolted together. Because GPU programming for HPC and technical computing and AI and such like is becoming much more important, they've started to manufacturers start to put these things together. So more modern, the most modern generation of GPUs, such as the Grace Hopper from NVIDIA, don't have this such a bottleneck. So on something like the Grace Hopper, we have some of these for development purposes, but they're not. But we don't have them generally available. Is you have separate CPU and GPU memory. Okay? The CPU and the GPU have separate memory, but you can access them uniformly. Sorry, you can access them directly. So you don't need to transfer data from the CPU to the GPU, and then you can the Hopper GPU can access the CPU memory, and the Grace CPU can access the GPU memory directly. They are physically distinct, but there's a layer which allows you to read and write directly to both memory spaces. So where the data is stored on CPU, GPU will therefore influence access time, but it is much simpler. You don't have to explicitly transfer them. So these super chips have unified memory between the CPU and GPU. You don't need to move data between the host and device. However, the location still does matter. And so we here see the way it works is that this is just the same diagram, that the system, the memory system translates between CPU, GPU, and GPU and CPU address spaces. And this is a kind of a diagram of what the access speeds are. But the main thing we would see is that the Hopper is the GPU and the Grace is the CPU. So if the CPU accesses the high bandwidth memory, it has very high latency and low bandwidth. If the GPU accesses its own memory, it has low latency and high bandwidth. And the opposite is true for the standard memory. If the CPU accesses the memory, it has very high bandwidth and low latency, but if the GPU accesses, it has low bandwidth and high latency. The most recent AMD architectures have genuinely unified memory. There's a single physical block of memory that the CPU and the GPU can access, which hopefully will make things much simpler going forward. And so, just for example, a very modern AMD might have 128 gigabytes of memory, but it's in the same physical location. Now, this isn't my slide, but someone's read the white paper, and it's not entirely clear how it's all laid out. But there is a lot of very high bandwidth available. But so there's a single block of high bandwidth memory. It's accessible by the GPU and the CPU, and you have many hundreds of gigabytes of memory bandwidth available to you. So that was a bit of a run through. I think the key concepts here are, so that's you may not be particularly interested in the hardware, but it's useful to understand that, understand how they work. But I wanted to summarize here the fundamental concepts, that there's potentially separate CPU and GPU address spaces. And that means, although there's very high bandwidth between the GPU and its own memory, you have to manually or by hand transfer data from the CPU to the GPU and from the GPU back. And we saw there with these like CUDA mem copy and copy in, copy out clauses, and that's an important thing you have to worry about. And on older and not so modern systems, that can be a bottleneck. The way that GPUs get their power is it comes from many thousands of CUDA cores or compute units in AMD, and each is a separate thread. And the threads operate in a SIMD fashion. And so though you have lots of threads, they operate in blocks and together. NVIDIA calls them warps, or AMD calls them wavefronts. It's standard vector or SIMD type processing, but it's not like doing a SIMD instruction of 4 or 8. You're doing SIMD instruction of 32 or 64. So unless you can get all your GPU threads to be doing the same thing at the same time, then you will not get good performance. And so that will be something I'm sure that that will be covered going forward, how you make sure that your program executes efficiently on this architecture. So I finished slightly ahead of time. Are there any questions? I said apologies, I haven't given these lectures before. I wasn't immediately sure of how long they would take, so I finished slightly ahead of time. So just to basically recap, I'm just trying to yeah, so I will share that. So that's the first session over. Then the next session is on Thursday in 2 days' time, where you will William will talk to you about how OpenMP works and crucially the data movement. As I said, the CPU and the GPU have potentially distinct memory spaces. There's CPU memory and GPU memory, and so you have to manage that movement. And then Michael and Luca will talk about more advanced topics and performance on Monday. And then Mark and Luca will talk about OpenACC on. Okay. So back to GPU for AI. So GPU for AI might use the same program models for HPC kernel. I suspect that. So I'm not an AI. So I suspect. So the reason why AI works well on GPUs is at the very lowest level, training involves lots of matrix operations of fairly large matrices. And you know, if you're using some AI framework, you'll write some Python code and that will be implemented. I would suspect on almost all systems currently, it will be the low level operations will be implemented in CUDA or HIP. So under the hood, there will be a library to do very, very fast matrix operations, and it will be a CUDA, maybe CUDA block CU blast, for example. So at the lowest level, AI usage is using I would guess, a kernels model, because actually AI, the heavy computational AI maps down to very few operations matrix. So that's why you can then spend your time writing a very, very highly optimized maybe CUDA version of the matrix operation. Does that answer your question? Well, it's called Chen number 2. So I just, you know, the libraries that underpin AI processing on modern supercomputer, modern GPU clusters will, I'm guessing, be written in CUDA. They'll be the lowest level kernels model. Bogdan says, if I operate on mixed rows are not what's 30, how much efficiency do I lose? That's a good question. I mean, basically, you would well, I mean, if you're doing it across, if you parallelized across the row, then you would, you know, you would basically you would lose. Well, if you had small matrices, you could do multiple. You could have the threads doing. If you had very, very small matrices, you could have each of the threads, you know, doing different matrices, for example. They wouldn't necessarily. So you could have, you know, thread 1 doing matrix 1, thread 2 doing matrix 2. But in principle, generally, you know, if you have 33, I'm being very naive here, but for general SIMD processing, it takes the same time to do 33 as it takes to do 64, because you have to do 2 instructions. Okay, when you do 33, you do one vector instruction for 32, another vector instruction for 32, in which 31 of them are thrown away. If you do 64, you do 32s. So naively, you would say that you lose almost a factor of 2 if you're. But if you have a large matrix, that's lost in the noise. If you have 1,000 by 1,000 matrix, it's not really a big deal. But for pure SIMD operations, you would lose whatever the remainder was that didn't fit into 30. Does that answer your question, Bogdan? I use Magnum. Yeah, so it may not be parallelizing in that way. It may be clever enough to parallelize. It may notice that your matrix isn't divisible by 32 and do something more clever. So, but was this Magma? Is this Magma for the GPU or the CPU? Sorry to be stupid. This is Magma for the GPU, is it? Yeah. Okay. Yeah. So as I said, so for a very naive parallelization would suffer from what I've just said. However, they make Magma's a very, very, very high spec and performant library, and presumably they've spotted that and they do clever things. So yeah, they clearly so a very naive implementation would suffer, but clearly there's things you can do to get around that. Also, by padding with zeros, you're also loading those zeros. So it might be that the problem is that although you throw away, if you don't pad, you're throwing away some of the computation. You're not loading all this data you don't need. That might. I mean, how much worse? I don't know. I don't know how big your matrices were, but how much worse were you getting? Ballpark. I mean, how many rows did your matrix have? Okay, but how many rows did you have? Was it many? I don't know. I just want to get a feeling for what was sort of how big was the number of rows compared to the sort of SIMD size of 32. Again, if you okay, 2 times worse. That's surprising. You can get other effects that, depending on how your memory access works, sometimes multiple of 32 can be bad because of caching and such like. So sometimes multiples of 32 are not good because they can mess up the way that caching works. It's complicated, but yeah, okay. I'm slightly surprised, but I don't quite know how Magma works. If it's a factor of 2, it could be memory, it could be to do with the way the caching works. I don't know. It's interesting. There was another question here. So yeah, so Maji's asked about how it works. So I'm not an expert, but what happens is that when you compile a kernel, it is compiled with a different instruction set architecture from the GPU. So the compiler, it's compiled on the CPU side, but not for a CPU instruction. It's compiled for the GPU. So there's lower level stuff. NVIDIA called it PTX, which is sort of like a GPU assembly language. So there will be a compiled version of the kernel which you can't run on the CPU. It's using the GPU instruction set. Then that is shipped onto the GPU, and then the GPU executes it. So the first time you launch a kernel, it can take a long time. A, it may compile it on the fly, and B, it may transfer it. But the next time, it's much quicker. So yes, the instruction set on GPUs is totally different from CPUs. Completely different. It's something called PTX. Well, and it's very different. Yes, it's totally different instruction set architecture. Does that make sense? Yeah. I mean, for example, let's have a look. access. No, okay, I'm just looking, so I shouldn't do it. What does PTX look like? Okay. That's what I need there. This is an NVIDIA page. Running about PTX. Oh, okay. Oh, there we. Here we are. Okay, here we are. So it's assembly. It looks like assembly, yeah. I mean, loads and moves and adds and things. So it's, you know, it's got a reading, but it is that is going down to a very completely different ISA from you would have on the yeah, I do. So, but I don't know. I mean, I really don't know what the answer is. Again, Magma is very, you know, it's very, very highly optimized. So yeah. Okay, are there any more questions? So I noticed that there was somebody who was having problems logging on. It was, I apologize, pronouncing it, Uruj. I don't know. Do you want help with the? Do you want help, Uruj, with the TOTP stuff, or with the MFA? Or are you happy just to sort that out?
Yeah, I just said that, and after that, I'm still trying how to log in because I just no, it's asking me about try to change the LDAP password now.
Yeah. So okay. So I can I can probably help you with. It is a bit confusing. So that's the end of the session. I will stop recording, but oops, don't want to.